Okay. Today we have a visitor from Lisboa, Erkko Lehtonen, Universidade Nova de Lisboa from Portuguese, and his talk is permutation groups and permutation patterns. Please.
Thank you for the introduction, and I'd like to first thank Jörg Kopitz for the invitation to give this talk at your seminar. Hello, Jörg. I would also like to mention that this talk is partly based on a joint work I did with Reinhard Pöschel from Dresden. All right, so let's go to the topic, permutation groups and permutation patterns. So this talk will combine two different points of view to permutations, namely the algebraic one of permutation groups and the combinatorial one of permutation patterns. Of course, permutation groups, they are a classical topic in algebra, and perhaps this will need no further explanation, but I'm going to talk a bit about permutation patterns first, just to give the basic definitions right. So what is a permutation? A permutation is a bijection on some set. And we say that we consider permutations on finite sets. We can take this set to be the n-element set of the first n positive integers, and a permutation of rank is just a bijection on the set from 1 to n. We can also view such a permutation as a word of length n, where the ith letter is just the image of I under the permutation. Okay. So what is a pattern of a permutation? So let sigma and tau be permutations, sigma of rank L and tau of rank n, L at most n. We say that sigma is a pattern of tau, or that tau involves sigma. If there is a scattered subword of tau, we can pick up some letters from the word tau, so that the resulting subword is order isomorphic to sigma. Let us illustrate this with a little example, but here I will go in parallel with a little graphical presentation. So of course we can draw the plot of the permutation. So here is a permutation on the 7-element set, and this is its plot or graph. It's a finite set of points in the plane. So now we can choose a scattered subword, the ones with the red letters in the graph. We just take a subset of the points. We remove the other letters from the word, but then we have to scale these letters to obtain the permutation on the 4-element set. So we just take the unique permutation of rank 4 that is order isomorphic as the word with this subword. And in this way, we obtained a pattern, an example of a pattern of this bigger permutation. Let me still go through this example in the graphical way. Recall that, so what is the property of the plot of the permutation? So it is a set of points in the plane with the following properties. There are no 2 points on any horizontal line, and there are no 2 points on any vertical line. There are no 2 points on the same vertical line because it's a function, and there are no 2 points on the same horizontal line because it's an injective function. And in fact, if we have any such configuration points we can on the plane, we can just ignore the scales. It is possible to see what is the leftmost point, the second from the left, and so on. This would give us the kind of the axis for the x direction, and it is possible to find the lowest, the second lowest, the third lowest, and so on. This gives us the labels for the vertical direction. And in this way, we can just take the plot of the permutation. We can just pick up a subset of points from the plot, and the resulting subset of the points, it will still have the property that there are no 2 points on the same horizontal line, no 2 points on the same vertical line, and therefore we can view this as the plot of some permutation on the smaller set. And this is what actually happened here. All right. So this pattern involvement relation is a partial order on the set of all finite permutations. And downward closed subsets of this pattern involvement relation are called permutation classes. So now, this diagram represents the set of all finite permutations, and it is partitioned into these levels, the ith level comprising the permutations of rank I. And here we have some permutations, sigma and tau as before, sigma of rank L, tau of rank N. And we had this relation, sigma is a pattern of tau. We can also take this permutation tau and take the set of all L patterns of tau, and we will denote this by pat L of tau, the set of all L patterns of tau. We might take also a set T of permutations of rank N, and we would take the set of all L patterns of members of T, and this we would also denote by pat L of T. We could go on the opposite direction. We could start with a subset of SL, a set S of permutations of rank L, and then we could go up to the N permutations. We would take the set of all N permutations with the property that all their L patterns lie within this given set S. We would call this set the set of N permutations compatible with S, and we denote it by comp N of S. And in this way, we get two mappings between the two levels in this diagram, between L and N permutations, comp and pat. And in fact, these two mappings constitute a Galois connection. Those who are familiar with Galois connections, this would be the monotone Galois connection induced by the pattern avoidance relation between these two levels in the diagram. And as such, as for any Galois connection, there will be the related closure and kernel operations, and the general theory of Galois connections tells us that there are certain nice equalities or subset inclusions that hold. Anyways, the point is that if we combine these two maps, I mean, we compose these two maps, pat comp will be a kernel operator and comp pat will be a closure operator. And then it might be interesting to see what the kernels and closures are. Okay. Furthermore, there is a nice property with these operators comp and pat. So we could start with some level L. We could go up to a level M and still higher up on the level N using comp. So this is what we do here. We start with level L, go up to M, and then N. But in fact, we could just go directly to level N with one step. So this is kind of a transitive property. And the same holds for the pat. We would start with the level N, then go first down to level M, and then still down to level N. We could just go to level N with a single step. Fine. So all this business about permutation patterns could be formalized in a nice way as follows. So we are now taking an n permutation tall, and for any subset I of cardinality L of the n element set, let Hi be the unique order isomorphism from this the L element set of first positive integers from 1 to L to this subset I. This is the L element subset of the n element set. So there is a unique order isomorphism between these two sets. They are naturally ordered. We can define a mapping tau I. So tau was a permutation on the n element set. If we first take this order isomorphism from the L element set to the subset I, then we apply tau to this subset, and then we go back to the L element set with the order isomorphism of the image of I. So the resulting map will be a permutation of the L element set, and in fact, this will be the pattern of tau corresponding to this choice of elements in the word that are indexed by the elements of the subset I. So the patterns of tau can be described in this nice way, or this is a very, very useful way of describing the patterns. So now we have the crucial observation. So there is a connection between permutation groups and permutation patterns that is perhaps not obvious, but this is the key point in my work here. So if we take any two n permutations, p and tau, any pattern of the composite of pi and tau is the composite of two patterns, or patterns of the respective permutations. And the proof of this is just a single line. Using the formalism that we just introduced, if you take the pattern of pi tau corresponding to the subset I, we just write down the definition. We have the permutation pi tau here. We compose with the order isomorphism Hi, and then go back with the order inverse of the order isomorphism with the image of I relative to this given permutation. But now we do the trick. we just introduce the identity permutation in somewhere in this composite of permutations. Let's plug it here in the middle. And of course, we write the identity permutation as the composition of some permutation and its inverse. And in this way, we can write this as the composite of the pattern tau I and the pattern pi tau of I. Well, that was the simple proof. This was a simple observation, but it has a crucial consequence, namely the following. So if we take any subgroup S of the set of L permutations, then the set of compatible N permutations of S, comp N of S, will be always a subgroup of Sn. And the proof, well, it's not too difficult to see this. So we just, so we assume that S is a subgroup of SL. We take two permutations from comp N. We need to show that comp N of S contains the composition and the inverses of the members of its elements. So by the definition of comp N, the set of L patterns of pi and tau are contained in S. And now let's see what we can tell about the patterns of the inverse of pi and the patterns of the composite of pi and tau. Well, the set of L patterns of the inverse of pi, it is well known that the pattern involvement relation preserves inverses. So this will be the set of inverses of patterns of pi. And similarly, if you take the patterns of the composite permutation, well, as we saw in the previous lemma, the patterns will be compositions of patterns of pi and patterns of tau. So this set will be contained in this set composition of the patterns of pi and the patterns of tau. And since S is a group, it contains these inverses and products of members of S. So these will be subsets of S, and therefore these two permutations, their patterns are contained in S, so they belong to the set of compatible permutations of S, comp N of S. So comp S is closed under inverses and compositions of its members, so it is a group. So this is a very nice result, which gives us the nice connection between permutation groups and permutation patterns. So now one could ask, so what kind of permutation groups arise in this way from the pattern avoidance or pattern involvement relation? What kind of permutation groups are of the form comp N of S for some sets S of permutations? Oh, I see I have here still a little remark. So the converse of this proposition does not hold. So there do exist permutation groups that are of the form comp N of S for some subset of the L permutations, but there is no subgroup of the L permutations for which this group is of the form comp G. However, if L is at most 3 and N is greater or equal to L, then it holds that for every subset S comp ns is a subgroup of Sn if and only if S is a subgroup of Sl. But this is a very, very special case. So now getting back to the question, what kind of permutation groups may arise in this way as the set of compatible permutations? And this was a question that I studied with Reinhard Böschel, and we succeeded in describing such permutation groups in terms of invariant relations. So recall that there is a Galois connection between permutations and relations. So this is the Galois connection induced by the relation of a permutation preserving a relation. So if we are given a permutation and a relation, we say that the permutation preserves the relation if the images of the tuples in the relation, when we apply the permutation component-wise, the resulting images will also be in the relation. And it is known, it's a well-known result that every permutation group can be described using this Galois connection. Every permutation group is the automorphism group of some relation or some set of relations. And with the help of these invariant relations, we were able to describe the permutation groups that arise from permutation patterns. The results are quite technical, so maybe I don't go to this in too much detail, but we had some results. So in order to describe a permutation group of the form comp n of S, it is sufficient to consider just Ellery relations if S is a set of L permutations. And moreover, we had a result, firstly, for groups of the form comp n of S for an arbitrary subset S of SL. So a group is of this form if it can be presented as the automorphism group of some set of permutations that satisfy a certain condition. So the condition is here, it's a bit technical, I don't go to this. So this was for comp n of S for an arbitrary subset S. And we had another result for groups of the form comp n of G, where G is a subgroup of SL. So here again, H is of this form if and only if H is the automorphism group of. But now we get a more concise formulation because it's a more restricted case. So now it is the automorphism group of a single relation, and we can describe somehow what kind of relation this rho might be. Okay. I'm not going to go to the details on this. Further details can be found in our paper, the reference of which is given here. But let me move on to another interesting topic related to these permutation groups and permutation patterns. Namely, I'm referring to the work on group classes by Atkinson and Beals. So a group class is a permutation class in which all the levels are permutation groups. So in these two papers, Atkinson and Beals were investigating group classes, and they obtained some nice results that I'm now going to review. So first of all, They showed what does the permutation class in which all the levels are groups look like. They describe the eventual behavior of such permutation classes. So let's see. If C is a permutation class in which every level is a permutation group, then this level sequence eventually coincides with just a handful of possible families of groups. And I'm going to call these families stable families. And what are these families of groups? The first possibility, the groups that I denote here by S, A, B of n. So A and B are some fixed parameters. And what is the group S, A, B of n? It is the group of all n permutations of this form, illustrated by this diagram. So in this plot, we have first the A smallest numbers. The A smallest numbers are mapped to the A smallest number. And then we have also the B biggest numbers in the set of the n elements. And we map the B biggest numbers to B biggest numbers. And everything that lies between the A smallest and the B biggest numbers, they will be fixed by the permutations. So SABN will be the set of all permutations of this form. Okay. The second possibility is the natural cyclic groups. This is the group generated by the so-called natural cycle of order n. So it is this permutation using the usual bracketing notation. It's permutation 1, 2, up to n. This is its plot, and the natural cyclic group is the group generated by this permutation. The third possibility are the full symmetric groups. This is clearer what this means. And then we have the families of groups of the form Gn delta n, generated by Gn delta n, where Gn is one of the above families, and delta n is the descending permutation. Written as a word, it is this n minus 1 down to n. The plot is this descending plot. And yeah, so what do we obtain when we take one of these groups together with delta? What does this generate? Well, with the full symmetric group, we don't get anything new because this delta n is already there. For natural cyclic group, what is the group generated by the cyclic group and the descending permutation? It will be the natural dihedral group of order n. And for the first case, we get something nice new, but in this case, we have to assume that A and B are equal. Okay, so this was the nice result. Atkinson and Beals described the eventual behavior of any group class. So we can have something in the lowest levels, but eventually our group class must coincide with one of these families described here. The second main result of Atkinson and Beals is this. So they described completely the group classes in which every level is a transitive group. So here are several possibilities. The first possibility is the class of all permutations. All levels are just symmetric groups. The second possibility we first have some symmetric groups up to some level, and then it's followed by natural dihedral groups. The second possibility, the third possibility, we have the symmetric groups up to some level, followed by natural dihedral groups, which are then followed by natural cyclic groups. So these were the first three cases. Then there may be some variations to this. The first variation, so we have the symmetric groups, and then we have the dihedral groups, but between them there will be two extra levels. There will be the alternating group, followed by what Atkinson and Beals called an anomalous group, and then come the dihedral group, possibly followed by the natural cyclic group. And here's another possibility. We have the symmetric groups, then we have some overgroup, the proper overgroup of the natural cyclic group, followed by natural dihedral groups, followed possibly by natural cyclic groups. And this is all. These are the permutation classes in which every level is a transitive group. So these were very nice results. However, there remain some open questions regarding this. Let's go back to the first result. This theorem reveals the eventual behavior of permutation classes in which every level is a permutation group. So we know that eventually we must reach one of these stable families. But this theorem does not tell us how fast this happens. What is the rate of convergence, so to speak? This theorem is also nice. It's a full description of group classes in which every level is a transitive group. How about other group classes in which not every level is a transitive group? And it was these two questions that I set forth answering. So the idea is we could take now, let's go back to our comp and pat operators. We can take an arbitrary group G of rank n, and then we can build up these sets of compatible permutation on every level higher. We know from our result that given any group G, these sets of permutations must be permutation groups on the respective levels. So we get new group classes in this way. And if our group G is not transitive, then we get something that Atkinson and Beals did not describe. And we would also like to know how fast this sequence of compatible permutations reaches the one of the stable families of Atkinson and Beals. We know that it must reach at some point one of those families, but how fast will this happen? So I had to divide this task into several parts. Different kinds of permutations required a little bit different treatment. there were a few easy cases like the full symmetric group, the trivial group, or the group generated by the descending permutation. Also, we can treat separately the alternating group. But then comes the case distinction between the remaining groups. The first distinction is made according to whether the natural cycle is contained in our group or not. So this would be the first case distinction. And for those groups where we do have the cycle, we have a nice description. As for the groups where we don't have the natural cycle, we have to make further case distinctions. The first distinction is made between intransitive and transitive groups. Recall that a permutation group is transitive if it only has a single orbit. Otherwise, it's intransitive. And for transitive permutations, we have to make further the distinction between primitive and imprimitive groups. So recall that a transitive permutation group is is it primitive or imprimitive? But the defining condition is if it preserves any non-trivial partition. Okay. I don't perhaps have time to go to all details of the results, but maybe I will quickly try to give you a little gist of what I did. So the results will be of the form. So given a group G, I would describe the group comp n+1 of G, because then we can use the transitive property. If we can describe comp n+1 of G for every group, then we can apply the transitive property, and we get all the levels higher up using these results repeatedly. So here are some lemmas concerning those easy, simple cases. So if the group contains the descending permutation, this happens if and only if comp n contains the descending permutation. Here we basically get some results that if the group contains the natural cyclic group, then the compatible permutations must contain the natural cyclic group. And in fact, these will be equivalent conditions. Similarly, for the dihedral groups, if G contains the natural dihedral group, then the compatible permutations must contain the natural dihedral group. And this is again an equivalent condition. Also, okay, I guess here are the simple cases. For the full symmetric group, the compatible n+1 permutations, they are just the all permutations. We get the full symmetric group. For the trivial group, we get just the trivial group. For the group generated by the descending permutation, we get the group generated by the descending permutation. So these are really easy cases that are quite easy to see. In what follows, I'm going to use the following notation. So if pi is a partition of n, I will denote by S subscript pi the set of all n permutations that map every block of pi into itself. The compatible permutations of the alternating group can be described quite in a nice way. So we can take the partition of the n element set into odd and even numbers. So using our notation from the previous slide, S odd even of n is the set of all permutations that preserve odd numbers and preserve even numbers. So they map odd numbers to odd numbers and even numbers to even numbers. Let us also denote by WOEN the set of all these permutations that swap the blocks of this partition, that is, they map odd to even and even numbers to odd numbers. We also have the alternating group, the even permutations, and let's denote by ON the set of all odd permutations. And now we define psi of n as the set of all even permutations that map odd numbers to odd numbers and even numbers to even numbers, and all odd permutations that swap the odd and even numbers. And this will be the compatible n+1 permutations of the alternating group of degree n. If we go higher up from this, if we go to the n+1 permutations from the n alternating group, then we have these four possibilities depending on the congruence class model n of n. So we have here the natural cyclic group, trivial group, natural dihedral group, and the group generated by the descending permutation. And these are already Atkinson and Beals' stable classes. So after that, we will remain in one of these families. For the groups containing the natural cycle, we get either the natural dihedral group or the natural cyclic group, according to whether also the natural dihedral group was already included in our given group. Of course, the full symmetric and the alternating groups are exceptions to this. They were already described. And these are Atkinson and Beals' stable families. So after this, we will remain. For the intransitive groups, let's observe that if you take an arbitrary intransitive group G, let's denote by orb G, the set of all orbits G. G is clearly a subgroup of the group S subscript orb G. So the set of orbits is a partition of the end element set. And this is the finest partition pi for which G is a subgroup of a group of the form S pi. For the group S pi, we can describe the compatible n+1 permutations in terms of partitions. So given a partition of the n element set, we define a new partition of the n+1 element set in the following way. So this is best illustrated by this example. So here is a partition of 14 elements. So we first find the intervals that are contained in a block of pi. So here we have 1, 2, 3, 4, 5, 6, it's contained here. From 7 to 10, it's contained here. 11, and this interval. So these are the intervals, maximal intervals contained in the blocks of pi. And then, given these intervals, we can build the partition on the n+1 element set we take each one of these intervals and we split it into two parts. The two parts will be the smallest element of the interval and the rest. But there are two exceptions. For the interval containing 1, this we don't split into 2. And the interval containing the largest element, we still take the block containing just the smallest element, but then to the rest, we also add the new largest element, n+1, so that we get a partition of the n+1 elements. And with this construction, we can show that the comp n+1 of S pi will be S pi prime, provided that the descending permutation is not in S pi. If the descending permutation is there, then we have to take the group generated by S pi prime and the descending permutation. And then this can be repeated. We can show that, okay, for groups of this form, if we go up taking compatible permutation, we will still have permutation groups of this form. Okay, and then we can quite easily determine how fast we will reach one of the stable sequences. I guess I'm soon running out of time, so maybe I will skip details. For the primitive groups, sorry, in primitive groups, we get quite a similar description. So in primitive groups, they are the transitive permutations that do preserve a non-trivial partition. And we take this partition and it plays a similar role in the description of the compatible permutations. The same construction of the pi prime applies also here. But here we have some additional permutations. I'm not going to describe this. And finally, the primitive permutation. This is something completely different. We have to explicitly describe the cases for n equal to 6. On the next level, we have, or these are the primitive permutation groups of rank 6, and their compatible n+1 permutations are these. For n different from 6, on the next level, we have this here. But then when we go from any of these groups 2 levels up, then we have the descending permutation, the generated group. Putting all this into a short summary. So what we showed here, we determined for every group, the smallest number n, for which the n plus m permutations belong to the Atkinson and Beals stable families of group. So this is kind of the convergence rate to the stable families. And if G is intransitive, then the convergence rate m is at most n-1. If G is imprimitive and the natural cycle is not in G, then m is at most the largest proper divisor of n, and in all other cases, m is at most 2. And of course, we described exactly what the groups are in these compatible classes. So let me conclude this talk by giving the references to the literature. So this is these are the papers by Atkinson and Beals that I mentioned, and the 2 papers on which I talked by Reinhardt, and this more recent paper on this improvements of Atkinson and Beals' result. So I guess this was all for today. Thank you very much for your attention.
Okay, let's thank the speaker for the nice talk. If you have any questions or comments, you can simply speak without asking a permission. I see that there are no questions. Okay. Unmute your microphone.
I have a comment.
Yes.
Okay, let's go.
So your work is very nice, and just to say something that it has a new significance, this work on permutations, on computability, on theory of computability, and on the top of that, typed theory of computability, which is introduced by Moskovakis. So there, the permutations are extremely important to special kinds of permutations under special conditions, which I think will give some of those, if you go, I forgot what they were called, but they can be clustered. The permutations can be clustered under the condition of some introduced ranking on sigma and tau. And I believe that sigma will carry the conditions for restrictions, and sigma, with these additional restrictions for acyclicity, will be sub, whatever you called it there, sub of tau. The tau will be the complete one, and sigma will be a cluster with conditions for acyclicity, and where each sigma will be assigned a special ranking. So that is my first immediate grasping of your work, but it has to be investigated, I guess.
Yeah, this sounds interesting. It's always nice to know about connections and applications. I'm not familiar with this field that you described.
This theory itself is a theory, it's mathematics, new kind of mathematics, of algorithms, formalization of algorithms. The notion of the notion of algorithm, we know it as Turing machine or generative grammar without any conditions, etc., etc. Emil Post systems and Markov algorithms, etc., etc. So Moskovakis has introduced a new theory, mathematics of the notion of algorithm.
Right.
And then this condition for acyclicity brings extraordinarily important theoretical work with significant applications. So I'm trying to navigate between development of the theory and finding possible applications. And I am 1,100% sure for one ongoing application to computational grammar of human language.
But Rusanka,
Also to compilers.
This already is several slidefuls of information. How can we handle this?
I said,
the situation we are now. Yeah.
I'm sorry to be so, but probably that's in my brain, in my mind, because I know what I'm talking about. But what I presented in the seminars in the department is actually theoretical application of this permutation groups.
Mm-hmm.
So there is one core group inside that carries isomorphic permutations under the condition of special condition of acyclicity.
Okay, Thank you for the comments, but maybe you can give sometimes another talk, or you can write something, etc., etc. But now, do you have any other questions?
No.
Or comments? If no, let's thank the speaker once again. About the next Friday, in the moment we still don't have any suggestion for a talk. If during the weekend there is some suggestion, then we'll have a talk the next week. Otherwise, we have in 2 weeks. The speaker will be Kislytsin from Barnaul, from the this is in Russia, and the talk will be in Russian, but the presentation will be in English, and it's something about ring theory. So the announcement will be in time. Okay.
So once again, thank you for this nice talk to me.
Thank you.
It was wonderful for me, because right now I have to do something with these permutations. When I submit the papers here and there, I just mention these permutations, write something there, and then people complain, you have to define them in details, but in details it has to be complete paper, separate paper.
Okay. If no other questions, no comments, you can continue to chat, but I have to go to another meeting. Sorry.
So I'll stop recording now.